How long would it take us to go to Jupiter? Jupiter is one of the most important planets in our solar system, with giant anti-cyclonic storms and a magnetosphere so powerful that it defies comprehension. Jupiter is an intriguing planet. Many people would prefer to go to Saturn, obviously, because of its beautiful rings. But Jupiter, too, won't disappoint you. There are many reasons to go to Jupiter, like its icy moons, which we will discuss later on in the video. But if you were to escape Earth for some reason, a cost-benefit observation would show that Jupiter is a more viable option. So why would we want to travel to Jupiter? One of the most compelling reasons to visit Jupiter would be its moons. Even though Jupiter is a gas giant, it has 80 rocky moons. It's almost like a mini solar system of its own. Jupiter's moons like Europa, Ganymede, Callisto might contain vast reserves of liquid water underneath their icy shells, and can be the best place to look for life in our solar system. So if we decide to go to Jupiter, how much distance would we need to cover? The journey to Jupiter is going to be a long one. Earth and Jupiter are like sprinters sprinting on a clay track under the scorching sun. Because they circle around the sun at different speeds, the distance between them varies all the time. The distance between them is approximately 365 million miles at their closest point, and 600 million miles at their furthest point. Just to give you an idea, 600 million miles is more than 24,000 times the circumference of the Earth. And to get a better idea of how far Jupiter is, it would take us approximately 800 years if we tried to travel to Jupiter at 70 miles per hour, which is the normal speed for our cars. The two celestial bodies are approximately 483 million miles apart on average. Keeping these things in mind, scientists must weigh the benefits of burning more fuel versus the significant cost outlay and time required to reach the goal. The time it takes to travel to a distant planet is determined not only by technical advances in propulsion technologies, but also by how all of the planets are aligned. Since we are talking about going to Jupiter, what about spacecrafts that have already been to Jupiter? There have been spacecraft in the past that have actually been to Jupiter. In the 1970s, 4 NASA spacecrafts, Pioneer 10 and 11 and Voyager 1 and 2, were launched. All 4 of them took a direct route to the gas giant. Even though all of these traveled to Jupiter, none of them stayed around. They used Jupiter's gravity assist, which flung them out towards the outer solar system. But in the past, there have been only 2 spacecraft which actually stuck around, Galileo and Juno. Both missions followed a more indirect route to Jupiter, relying on the gravitational pull of the inner planets to accelerate through the asteroid belt and into Jupiter's orbit. Taking the long route required less fuel, which is required to slow down sufficiently to establish a stable orbit. So how long did these trips take? NASA's Pioneer 10 was the first spacecraft to reach Jupiter. It traveled the shortest route possible, taking only 640 days, just under 2 years. Despite this, it barely arrived within 130,000 kilometers of Jupiter. When a spacecraft just intends to observe the planet superficially, it takes faster paths. Pioneer 10 probe took a few photographs of Jupiter before continuing its journey towards the outer solar system. In a similar fashion, Pioneer 11 and Voyagers 1 and 2 took roughly around 600 days, but were able to reach much closer to Jupiter than Pioneer 10, getting within 22,000 kilometers of the gas giant. The Galileo mission, which was launched by NASA with the specific goal of researching Jupiter and its moons, was the first space mission to spend several years orbiting the planet. To stay close to the planet, a spacecraft must travel slowly and follow a more roundabout route in order to enter Jupiter's orbit and conduct its inquiry. A too fast spaceship would simply fly past the planet without entering its orbit. The Galileo mission took 2,242 days, nearly 6 years to reach Jupiter, but it did it at precisely the appropriate velocity. Galileo, the first spacecraft to spend several years in Jupiter's orbit, used a Vega, Venus-Earth Gravity Assist course. The spaceship had one near contact with Venus, then 2 rounds about Earth before being hurled off like a disk towards our solar system's main planet. The fastest any spacecraft traveled to Jupiter was the New Horizons probe, which traveled around 45,000 miles per hour, reaching the giant planet in only about 405 days. On its approach to Pluto and other minor planets, this space probe had an unusual flyby. It took advantage of Jupiter's tremendous gravity to increase its speed and optimize its path towards the dwarf planet Pluto. The gravity assist from Jupiter helped New Horizons increase the probe's velocity by approximately 8,700 miles per hour. This helped in truncating its trip to our solar system's beloved dwarf planet by 3 years. If we talk about sending humans to Jupiter, there might be quite a few other things to keep in mind, and the missions would also take a bit longer than the spacecraft. The farthest humans have been in outer space is the Moon. We haven't been back to the Moon also for the last 50 years and are finally returning now thanks to the Artemis missions. According to NASA, the shortest, most fuel-efficient path to Mars would take 9 months one way and 21 months round trip. If we generalize the methods used to compute this path, a similar one-way trip to Jupiter would take almost 6 years. NASA also predicts that a 4-person crew would require 8,000 pounds of food every year, implying that a 4-person mission to Jupiter would require 48,000 pounds of food simply to get there, and significantly more to return. In addition, all of the life support and research equipment would have to be sent into orbit from Earth. On top of this, we would also need to reach Jupiter safely. Astronauts would face a lot of challenges. One of the biggest one being radiation. Aside from the continual bombardment of radiation from the Sun, which is unprotected by our magnetosphere, space travelers will have to shield themselves against galactic cosmic rays, which can cause genetic damage and cancer. Astronauts will also face various psychological issues while spending lots of time in space. Long-term spaceflight can cause anxiety, which might exacerbate interactions with other crew members. Isolation from family and friends, along with a routine work schedule, exacerbates these symptoms. Even though astronauts are trained for this, they are trained on Earth. Once you go outside of our home planet and see the blue marble floating in space, it changes your perspective. Thanks to NASA's new generation suits and the upcoming Artemis missions, these challenges will be perfected and improved upon in the coming years. While traveling to Jupiter, there is also the route which scientists have to keep in mind. A spacecraft can travel a straight path, like the Pioneers and Voyagers did, or a longer, more roundabout path, like Galileo or Juno. A lengthier trip would need them passing close to a planet's orbit. This is why their alignment with respect to each other is of critical importance. The planet's gravitational pull lures a spacecraft inside when traveling towards it, and then slingshots it on its way around and back out. The spacecraft has to rely on the planet's orbital energy to achieve this. The loss of energy is so tiny that even though the planet loses some amount of its energy, the retardation in motion is negligible. At last, there is the question of which is a more efficient method to reach Jupiter. While you may get to Jupiter faster and in less time by burning more fuel, there is a more fuel-efficient method that will save you a lot of money and other valuable resources. Furthermore, money isn't the only barrier in this situation. Satellites moving at high speeds also struggle to slow down to the proper velocity and settle into a celestial body's orbit. However, spacecraft, like any typical trip through a low-lit planetarium giving you a tour of the solar system, are built to speed by planets with the goal of only glancing at the planet and taking a few shots before flying off to explore the unknown ahead. This is known as a flyby. Jupiter is one of the most active and interesting planets in our solar system. Jupiter's moons, which have enormous seas behind thick ice shells, may just provide the right environment for life to develop and are among the top contenders for life outside of Earth in our solar system. Fortunately, we have 2 major space missions planned to visit Jupiter's moons. The first is NASA's Europa Clipper, which was created expressly to examine Europa, one of Jupiter's 80 moons. It's scheduled to launch in 2024 and is expected to reach Jupiter's orbit by 2031. As previously explained, in order to remain in Jupiter's orbit, the spaceship must follow a long meandering course with reduced velocity, rather than just whizzing past it. Another project, the Jupiter Icy Moons Explorer mission, is planned by the European Space Agency to launch in 2022 and reach Jupiter's orbit by 2029. In brief, an extremely fast spaceship like New Horizons can reach Jupiter in a little over a year, but if the goal of the space mission is to only fly past Jupiter, it would take roughly 550 to 650 days on average. To examine the planet and its moons by entering Jupiter's orbit, a spacecraft must be slow enough to reach Jupiter's orbit at precisely the appropriate speed, allowing it to be caught by the gas giant. The gas giant has many things to offer us and will be a valuable resource to understand about our solar system. How long would it take to go to Saturn? Saturn is one of the most beautiful planets in our solar system. Its rings are one of the most differentiating features. It's often seen as a hazy yellow planet in the night sky and feels so close when we observe it with binoculars or a telescope. But in reality, it is much farther away. Saturn is one of the most beautiful and intriguing planets in the solar system. It has piqued the interest of scientists for decades, if not millennia. According to Laplace's theory of cosmogony, it depicts an early stage in the development of the solar system. However, this is not the only reason that Saturn fascinates people all around the world. Scientists were also hunting for solutions to other problems, such as how Saturn acquired its rings. Why are the circles different colors? What are the source of its faint self-luminescence? Is there a greater number of moons orbiting Saturn? And then there are moons of Saturn which are even more intriguing to scientists. Courtesy of the Cassini mission, which we will come to shortly, scientists were able to witness phenomena that had never been seen before. Titan, a moon of Saturn, is also a contender for possibly harboring life. Even other moons of Saturn, like Enceladus, make the exploration of Saturn even more exciting. Owing to all these reasons and a possibility of a human base on one of Saturn's moons, exploration of Saturn might one day become humanity's major goal, like exploration of Mars. In order to go to Saturn, we first need to understand how far away Saturn really is. Would it take a long-haul trip for us to get to the ring planet? What challenges will a human voyage face? Let's not get ahead of ourselves and start with the very basic. The distance of Saturn from us. Saturn, like our planet Earth, has an elliptical path around the Sun. Its orbit is tilted 2.4 degrees relative to Earth's orbital planet. As a result, finding the distance between the planets is no easy feat. Just like getting to a place on Earth might take varying lengths of time depending on the path you take, getting to Saturn can take different amounts of time depending on which route you choose. As both planets travel through space, the distance between them changes all the time. They are around 746 million miles or 1.2 billion kilometers away when they are the closest, or 8 times the distance between the Earth and the Sun. They are a little over 1 billion miles or 1.7 billion kilometers apart at their most distant, when they are on the opposite sides of the Sun from one another, or 11 times the distance between the Earth and the Sun. Because the planets move into ellipses, distance between them may vary significantly at a certain point of time. According to research, the closest distance between Earth and Saturn was 1.201 billion kilometers on December 21, 1914. Cassini and other spacecraft cannot be launched straight to Saturn. They are too hefty and insufficiently strong to slow down when necessary. Instead, Cassini was heading towards Venus and passed by it twice, once by Earth and once by Jupiter. These flybys provided Cassini with enough power to accelerate, utilizing the gravitational attraction of each planet. Saturn travels through space at more than 21,000 miles per hour and takes 29.5 Earth years to complete one circle around the Sun. Earth passes Saturn in its spin a little under once a year, causing Saturn to seem to travel backwards in the night sky as our planet zips past it. When it comes to traveling to Saturn, there have been many previous spacecraft that have been sent to the planet. All took different amounts of time to reach Saturn depending on the route they took. We have already talked about the distance of the planet from us. Using these numbers, we can figure out how long it would take to get to the gas giant. And when we talk about getting to a planet, it's always nice to talk about probes and missions that have already been sent to Saturn. A total of 4 missions have covered the distance to the ring planet. 3 of them were flyby missions, whereas Cassini-Huygens was a dedicated mission to Saturn in orbit from 2004 to 2017. When spacecrafts are sent, scientists have to decide on which route to take. We can get to a planet faster and in less time by burning more fuel. There can be fuel-efficient methods that will save a lot of money. Furthermore, money isn't the only barrier in this situation. Satellites moving at high speeds also struggle to slow down to the proper velocity and settle into a celestial body's orbit. However, spacecraft, like any typical trip through a low-lit planetarium giving you a tour of the solar system, are built to speed by planets with the goal of only glancing at the planet and taking a few shots before flying off to explore the unknown ahead. This is known as a flyby. The 3 flyby missions were by Pioneer 11, the Voyagers, and the New Horizons mission. Pioneer 11 was launched in April of 1973 and traveled nearly 70 years to reach Saturn, arriving in 1979, taking about 6.5 years to reach Saturn. Voyager 1 was launched in 1977, and it took 3 years and 2 months to arrive at Saturn in 1980. Voyager 2 was launched a month before Voyager 1, but it did not arrive at Saturn until August of 1981 and took 4 years. The Cassini-Huygens spacecraft was the spacecraft that took the longest to reach Saturn. It was launched in 1997 and arrived at Saturn 7 years later in 2004 by utilizing the gravitational pulls of neighboring planets. The New Horizons probe was the quickest to reach Saturn and only took 2 years and 4 months to reach it. But why is there such a difference between the time taken by these spacecraft? There are many factors that influence the time taken to reach a planet in our solar system. As we mentioned above, scientists have to decide on the route and method to take while launching a space probe, and there are other factors too. The first major deciding factor is whether the spacecraft is launched directly towards Saturn or is it sent towards another celestial object of the solar system and has to only use Saturn's gravitational potential energy to slingshot itself. Before reaching Saturn, several spacecraft are launched towards other celestial objects. Another important factor to consider is the sort of engine driving the spacecraft, whether it is fuel efficient or not. And a third factor to consider is that slowing down takes a long time. So if a spacecraft is only going to fly by, it must slow down. But if it's going to orbit, its voyage to Saturn will take longer. This is where the definition of flyby we explained earlier becomes important while understanding the various routes to Saturn. With such considerations in mind, let's talk about these previous missions to the gas giant. Before reaching Saturn, Pioneer 11 and Cassini utilized the gravitational pull of many planets. Other planet flybys added years to their journey. Voyagers 1 and 2 moved far faster through the solar system, making their first sightings around Saturn. The New Horizons spacecraft has numerous notable advantages over the other stated missions. The primary differences are that it has the most sophisticated engine available and was launched on a single trajectory past Saturn on its approach to Pluto. It is vital to realize that in space, you do not travel in a straight path. The majority of time spent traveling is spent slowing down. If you do not slow down, you'll fly beyond Saturn into deep space, because Saturn's gravitational attraction will not be able to bring you in. But that was the time taken by the space probe to reach Saturn. What about sending humans to Saturn? Could we shorten the journey? If we talk about sending humans to Saturn, there might be quite a few other things to keep in mind, and the missions would also take a bit longer than the spacecraft. There are many factors to be taken into account. Number one being the mass traveling to Saturn. Robotic spacecraft are quite heavy, and adding humans, along with food and water to survive, may treble the weight of the spaceship. It implies you need double the power to launch safely. NASA also predicts that a 4-person crew would require 12,000 pounds of food every year, implying that a 4-person mission to Saturn would require approximately 72,000 pounds of food simply to get there, and significantly more to return. In addition, all of the life support and research equipment would have to be sent into orbit from Earth. Taking all of this into account, it would take humans at least 8 years to reach Saturn. But you also have to think about the trip back. All of the spacecraft that have been launched have leveraged Jupiter's gravitational force to their advantage. When you get to Saturn, you may have to wait a long time for Jupiter to be in the proper position to provide power to the spacecraft. On top of this, we also need to reach Saturn safely. astronauts would confront several difficulties. One of the most serious is radiation. Aside from the constant assault of radiation from the Sun, which is unprotected by our magnetosphere, space travelers must protect themselves against galactic cosmic rays, which can cause genetic damage and cancer. Astronauts will encounter a variety of psychological challenges when spending extended periods of time in space. Long-term spaceflight can generate anxiety, which can make relationships with other crew members more difficult. Isolation from family and friends, as well as a regular job schedule, aggravates these symptoms. Even though astronauts are trained for this, their training takes place on Earth. When you leave our home planet and witness the blue marble floating in space, your viewpoint alters. Thanks to NASA's new generation suits and the upcoming Artemis missions, these challenges will be perfected and improved upon in the coming years. As we talked about in this video, there is no straightforward answer to how long it will take to get to Saturn. Even with New Horizons smashing records and crossing the trip in under 2 years, scientists plan to improve on the speed and time taken with stronger engines and more efficient flight patterns. In the future, the time taken to reach Saturn might be shortened by a lot, and interstellar travel might be as smooth as taking a vacation abroad. We never know, especially with the rapidly evolving technology. The long journey ahead to Uranus. Uranus, 7th planet in the solar system in order of distance from the Sun, 3rd in diameter and 4th in mass. Average distance from the Sun, 2.871 billion kilometers. Orbital period, 84 years. Equatorial diameter, 51,100 kilometers, exactly 4 times that of Earth. Mass of 14.6 times that of Earth. Rotational period, 17.25 hours. Minimum temperature, minus 226 degrees Celsius. 27 satellites detected so far. A hostile and violent world. Already flown over by one of our probes many years ago. A world full of mysteries. And we are about to return to it. Above us, hidden in darkness, the blue giants Uranus and Neptune are claiming our attention. Much larger than Earth, than Mars, than Venus, yet so distant as to be invisible to the naked eye. We encountered them only once when Voyager 2 flew over them in 1986 and 1989, then passed on until they were lost in interstellar space. Numerous other probes since then have visited all the other planets in our system, but the blue giants have not. They have been kept on the sidelines, even though we have long known that in them lies the key to understanding how our solar system, and especially the solar systems of other stars, came into being. Now, however, there seems to be a desire to return to Uranus, and that is a good thing. Countless, in fact, are the mysteries surrounding the 7th planet in order of distance from the Sun. Uranus is characterized by a rotation around its axis, unique in the solar system, an atmosphere agitated by winds at extreme speeds, and an extremely complex magnetic field, all phenomena whose origins are not well understood. It is also unclear in what part of the solar system it was formed, whether it ever exchanged positions with Neptune in the system's turbulent early stages of evolution, nor what its exact composition is and how extensive its rock and ice core is, while it is suspected that some of its major satellites, Ariel and Miranda, which show signs of geological activity, may harbor oceans beneath their surfaces. If we tell you this, it is for a very specific reason. But let us first do a little history, just to get a better understanding. From the beginning of time until the evening of March 13th, 1781, human beings knew of only 5 planets, those visible to the naked eye and now bearing the names Mercury, Venus, Mars, Jupiter, and Saturn. Although it is also visible to the naked eye, like the other 5 planets known since antiquity, it was not recognized as such and considered a star until the 18th century because of its low brightness and particularly slow orbit, and was identified as something other than a star only on March 13, 1781 by William Herschel. Curiosity about his discovery is that it came completely unexpected. Planets visible to the naked eye up to Saturn had been known for millennia, and no one suspected the existence of other planets until Herschel's discovery, who noticed that a particular low luminous star seemed to be moving. From then on, no one was sure of the real number of planets in our solar system. That wasn't until between 10 and 11 o'clock at night on that March 13th, the Anglo-German astronomer William Herschel spotted a small blue-green disk in his telescope. Following it and noticing day after day that it moved across the sky, Herschel was thus the first human being to reveal that new invisible worlds orbited the Sun. Or at least so the encyclopedias say. But was Herschel really the first to see Uranus? No. Other astronomers in previous decades had seen it, but all had mistaken it for a star without having the patience to observe whether or not it had its own motion and moved on. Instead, Herschel was the first to identify in that fuzzy little star a moving object. But did he immediately realize that it was a planet? No again. At first, he thought it was a comet, like the ones his sister Caroline discovered. And it took long periods of observations to get enough data to construct its orbit and to confirm that after millennia, the solar system had been enriched by another component. Like Earth, Uranus and Neptune are blue worlds. Neptune, on whose globe of marine color run white clouds, would also seem to the casual eye to be a clone of our planet. The blue of these planets, however, is not that of an ocean, but is the color of methane inside an icy atmosphere of hydrogen and helium at 220 degrees below zero, the coldest places in the solar system. Their strangely terrestrial hue, so different from the orange-red seething of Jupiter and Saturn, tells us that while they are two giant balls of gas, they are actually quite different from their larger cousins. Like Jupiter and Saturn, in fact, Uranus's atmosphere is full of hydrogen and helium, but with abundant presences of methane, ammonia, water, and hydrogen sulfide. Methane gas absorbs light in the red part of the spectrum, giving Uranus its blue-green hue. If you flew down through the layers of the atmosphere, the surrounding clouds would become denser and denser, colder and colder, bluer and bluer, as the gases absorb more of the visible spectrum. And beneath the atmosphere might be found the answer to another of Uranus's great enigmas. Its unruly magnetic field is tilted 60 degrees from its axis of rotation, much stronger at one pole than the other, and shifted a few thousand kilometers from the center. Some astronomers believe the warped field may be the result of vast oceans of ionic liquids hidden beneath greenish clouds, filled with water, ammonia, or even liquefied diamond. The two blue giants have their own distinct personalities. When Voyager 2 flew over Uranus, its photos amazed astronomers, not because of what they showed, but because of what was missing. No bands, storms, spots, or clouds, just a homogeneous pale turquoise sphere. Only by altering the contrast of the images could very thin clouds be discerned. Today we know that in fact Uranus is not so calm, thanks to infrared observations, and later telescopes have noted that storms have arisen, but it remains the most serene giant among the planets known to us. On Neptune, however, no apparent calm. It blows the strongest winds in the solar system, 1,700 kilometers per hour, 3 times the strongest wind ever recorded on Earth. Storms and bands and clouds are clearly visible, and all this turbulence keeps Neptune bright blue. In fact, Uranus is faded because of a permanent photochemical smog, which on Neptune cannot accumulate due to the stirring of the atmosphere. But what is the reason for this difference? Well, apparently the reason lies in the fact that Uranus is the planet that releases the least internal energy in the entire solar system. That heat that burns at the center of the planets, a relic of their formation. Uranus either does not transmit its heat or it has lost it, and both options involve more questions than the answer. There is one possible solution, and that is that the interior of Uranus was disrupted by a giant impact. This would also explain one of the planet's most bizarre features. The axis of Uranus is tilted relative to its orbit by 98 degrees. It's basically lying down, like an inverted spinning top rolling on a table. This causes Uranus's poles at the solstices to look alternately straight towards the sun, and are thus the places with the longest known days, 42 years of sun followed by 42 years of night. The most immediate explanation is that Uranus was knocked down like a skittle by another celestial body as big as or bigger than Earth. In fact, today some speculate that both Uranus and Neptune were struck in their infancy by planetary-sized bodies, Uranus by a smear while Neptune in full. If so, it would be confirmation that the entire solar system was sculpted at its origin by immense cataclysms. Which ones? Today we know that the planets we know are unlikely to have formed in the orbits in which we still find them. This is told to us by the moon we have in the sky, most likely born from the remains of the crash of a planet the size of Mars with the primordial Earth. This is told to us by the fact that 3.8 billion years ago, young but now formed planets suffered an immense asteroid barrage, the so-called Late Heavy Bombardment. Computer models also tell us that billions of years ago, the giant planets performed a complex gravitational dance before arriving at their present orbits, hurling asteroids around like gravel kicked by a child. According to some of these models, during the formation of the solar system, Neptune was closer to the Sun than Uranus, and all the planets were still much closer to our star than they are now. The only way to understand what really happened is to see whether the blue giants have retained traces of their past history. For example, to understand whether they formed where they are now or in warmer parts of the solar system. But it doesn't end there. Uranus and Neptune are surrounded by a large number of moons, also among the most exceptional and mysterious in the solar system, as well as thin rings. We associate the word moon with the idea of a dead, gray body like our own, but the major moons of Uranus and Neptune appear to have been active. The 5 major moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, are bodies of rock and ice between 500 and 1,500 kilometers in diameter that, in the few grainy images sent back by Voyager 2, often show signs of active geological phenomena and a young surface, capable of sculpting valleys and escarpments like Miranda's Verona Roots, the highest abyss in the entire solar system. A place where one can launch oneself off a 20-kilometer high vertical cliff and fall with exasperating slowness for 12 minutes before hitting bottom. What really happens, however, on those moons, we do not know. The moons of Uranus tell us that, as opposed to the hot geology of the terrestrial planets made of lava and rocks, there's also a cold but no less interesting geology drawn by ices and oceans of water, methane, and ammonia instead of mantles of molten rock. All features have always been considered interesting, though not intriguing enough to merit special attention, until astronomers began studying planets around other stars and discovered that ice giants like Uranus and Neptune were everywhere. In short, there are plenty of reasons to visit the blue giants again. So much so that the U.S. National Academy of Sciences recently issued a report urging NASA to plan as soon as possible to send a probe to Uranus. And that means that in all likelihood, the next high-profile mission will be the one that finally brings a probe into orbit around our home planet's most mysterious and most underrated planet. A mission that already has a name. It will in fact be called Uranus Orbiter and Probe, and it will aim to put a satellite into orbit around Uranus, which will observe in detail the planet's characteristics for several years, while also launching a probe into its dense atmosphere. Of the proposed missions, Uranus was chosen because over the next 10 years, there is no possibility of a useful trajectory for sending a probe to Neptune. In the case of Uranus, on the other hand, there would be 2 possible windows, in June of 2031 and April 2032, both with the possibility of exploiting Jupiter as a gravitational slingshot for a journey of about 13 years. To reach the goal, the mission would have to be approved and development work begun by 2024. Other launch windows between 2032 and 2038 would require trajectories to the inner planets in search of other gravitational assists, and the trip would take more than 15 years. That leaves NASA a decade to design the probe and raise the $4 billion needed to build it. We're not talking about tomorrow. We will have to wait more than 20 years before we receive images and data from such a distant world. By that time, we should have landed on Mars and put permanent bases on the Moon. It will be an era of exciting achievements. Let's keep our fingers crossed then, and let's all look forward to those happy days in the future.